Okay, everyone is here, I think. Let's go down a bit. So any questions that you may have so far? Okay, so then I think we can start. So we are studying right now the consensus theorem. Last time we started to talk about convenience, and so now we are here, consensus theorem. So it puts together the two notions we have studied so far, right? Regularity equals flatness of Frobenius. Right? In what context? You need to have a rank R defined over Fp in a theorem. Okay? So last time we started with the proof of this result. We started with one direction, which is considered to be the easy one. So last time I explained a proof that was maybe a little bit confusing. So I think I can give you, maybe we can go through it, and I'm going to give a tweak of that proof that is much easier. So what I said last time wasn't necessarily complicated. It was true, but there is a simple way to see things. So let me move, which is the following. So it has to do with the following. So last time we proved this. So we proved that if you take the polynomial ring over any field, so its Frobenius push forward is free. But it's not just free, it has a very peculiar basis. So it says that this is a direct sum of the following shape. So what we do here is that, first of all, we have to choose a basis for this field over K. So this is just the Frobenius of the base field, right? So you choose a basis. So choose a basis. Actually, it can be chosen to be a P basis if you recall your field theory class. But let's just choose a basis. Let's call it lambda. So this is a whole bunch of lambdas. It could be infinite, right? So the point is that K1 over P, well, it's a vector space, so you can always choose a base, no matter how large it could possibly be. So you can say it's lambda 1 over P, and you have lambda in lambda with lambda. Big lambda could be a ridiculously large set, but it's a set. So what you do here is that you take these monomials, and so you do two things. And so you take these monomials to go from 0 to q minus 1. This part here is finite, and there will be an infinite component coming from the residue field, or from this base field K. And so you have to put here lambda. Now you have to say that lambda isn't lambda.
Where does the Q come from?
The Q?
Which is any criteria like in order to have a boundary.
Q. Yeah, this Q. Yeah. This Q is equals to P to the E. Okay. So we're iterating Frobenius E times. So what F to the E does is it takes R and it sends it to R to the Q.
Okay.
So Q is just P to the E by definition. It's just a shorthand notation. Okay. Yeah. So you have this free decomposition. And it is free. So the Frobenius of the polynomial ring is not just flat, it is free, which is much stronger. And actually, if you choose a p-basis for your base field K, then you get a p-basis for the whole thing. So a p-basis, by definition, is just a sequence of, in this case, n elements, such that something like this is true. So I could have chosen p-basis here, and I can just put that in here, and I get a p-basis for the whole polynomial ring. It's something that's going to come up all the time, actually, this p-basis thing. Okay, but you have this decomposition. The problem is that then what you can do is that you can complete. So, okay, then, so something you can do is that you can localize. And localizing is a very nice operation, so it's going to commute with this direct sum. So out of this, right, you can take the maximum ideal of x1 through xn, and then you can localize. And you know, we saw last time Frobenius commutes with localizations. So you get a decomposition for R localized at M, right? And it's going to be the exact same thing. Then they use multi-index notation. You buy this. And now we may want to compute the Frobenius of this guy. So now we may want to take the completion, right? So that we can compute this Frobenius, the Frobenius of this ring, right? And so we saw last time, it's an exercise, that Frobenius commute with completion. So we may take the completion of this to get this. So, however, the completion of a free module is not necessarily free. It's flat. So this is a theorem. It's hard to find in the literature. But it is in the stack project, for example, and it says the following. So if you have M on R, let's say it's over a local ring. So let's say a module over a local ring, then we can complete it. So if this is flat, then M hat is flat. It's not obvious at all. It's flat R hat much. But the same isn't true for freeness. It's not true for projectivity. This is a subtle detail, but it's a very important one to understand why the flatness of Frobenius is more important than its projectivity. Because you see, like here you have a free module for the polynomial ring. Well, when you complete, what you get is just a flat structure. You don't get the free one necessarily. So what that means is that, you know, putting these things together, the only thing you can conclude is that the Frobenius of this ring is flat. Well, over completion. So this proves that the Frobenius of the power series ring is flat, but not necessarily free. Okay? However, if this big set lambda was finite, suppose this is finite, what does that mean? This module is finally generated. Therefore, the completion of that module will coincide with the base change. And in that case, if this is free, you can conclude that this is free. So that's an exercise. So there is a particular case in which this is free, which is the case if the field is finite. So remark, this is the subtle thing. If the degree of this extension is finite, then this module here is locally free or free projective. And you can inherit the same basis and therefore a p basis essentially. Question, what about the converse? In other words, is it true, and this is a genuine question, is it true that the only way in which this can be free is the only way in which this is free given by having a field whose Frobenius is finite? I asked around last week and I couldn't find an answer anyway. So it could be an open problem. But I don't know the answer. I suspect it's true that if this guy happens to be free, in other words, projected, because we're in a local ring, if it is projected, it is because it is F-finite. That's the notion. It is because this field here is F-finite. But it's something you can try to think about if you feel like so. This is to be a subtle thing. Okay? So that's what is behind the subtlety we were talking about the other day. And so from this, you can see how to prove the easy direction of the Kunz's theorem. Right? Because, so now let's come back to the proof of the Kunz's theorem. The easy part. Struggle with this. Maybe there's no boundaries. So there is an easy direction, which is this: regularity implies flatness. How you do this? So there you are, right? If you start with something regular, we know that by the Cohen structure theorem, it's gonna be of this form. It's gonna be a ring isomorphic to the power series ring, and we can verify that the Frobenius is flat. That's what we just did, right? So last time we saw that if you want to prove that the Frobenius is flat, you can localize because flatness is a local property, and you can complete. And there you are. So what I did last time is that I explained an argument to show that this is flat, but it can also be seen as well. Okay. Now ready to the hard part? Is everyone happy with this direction?
Yeah.
Okay. So let's get to the other one. Let's go through this proof, okay? So okay, we're gonna need some preparation. So we need to talk about the circle. Which in Spanish, I think it translates to zócalo. which is some sort of base, right? What is the so-called? It's a base, right? Like for a statue or something like that.
Oh.
Okay, so I think that's what you're trying to make. So the definition is as follows of this notion. So what you do, so you need the following. You need a local ring. Local ring. And the other thing you need is a finally generated R module. From this, you can compute a suckle. So this gives you a suckle of M. And by definition, it is a submodule of M. And what you do is that you take all the elements of M such that they are killed, or in other words, they kill the maximal ideal. So here, you really need to have a good handwriting, so many M's. So the elements of M, you can think about that they kill the maximal ideal, or that they are killed by the maximal ideal. But they don't get along with the maximal ideal, okay? It is a submodule. And this is the humble definition, but the more conceptual one is homological in nature, because it is the home. Well, technically speaking, this is an isomorphism, the canonical one. So what you do is that you look at the maps from the residue field to M. Okay. Right? Because what is the point? The point is that the field K is generated by one. It's generated by one element as an R module. Right? K is literally R modulo M. So what does it mean to hook up a map from here to here? Well, all you have to do is to decide where to send one. Because when you have, chosen where to send one, that's the choice of an element here. But for the map to be well defined, it has to respect the relation that N kills that element, right? So that's why these two things are the same. So if you want, like, there is a very well defined map from here to here, which sends N to the map that sends 1 to M. And if you think about it, it's this injective and subjective. And this module here, in more homological terms, is just the first x0 of Km. Okay. So why is the suckle a thing? It's because of the following observation. Let's go all the way to the other side. Okay, there is that suckle guy. So, in particular, this is the observation. In particular, the depth, remember the depth of M was like that, minimum I such that the x I Km is non-zero. So if you think about that, then the depth of a module is 0, if and only if the suckle of M is not 0. In other words, you can find an element of M that's not 0 and kills the maximal ideal. So you can find a non-zero divisor. That's the point. So in that case, so if, well, in particular, N is not 0, right? So in particular, N is not 0, right? And which means, right, in this setup, that when you look at this intersection, this is non-zero. That's a theorem, right? It has a name. I always forget what is the name of this theorem. It's like Crew's intersection theorem or something like that. So the point is that being zero on a regular local ring is that you live in these modules for all n. That's the point. It's quite, but it's sort of intuitive. Like, so well, this is non-zero. Yes. Actually, there's a typo here. No, sorry. What am I saying? I'm being stupid. Sorry. I got confused myself. No, what is true? What am I saying? So what is true is that this is always zero. Right? So the conclusion is like if the depth of n is zero, so it means, well, this is non-zero, and therefore it cannot be in the intersection of all these modules, right? So it implies that there exists some magical n such that the socle of n is not contained in n . Is that okay? Depth of m equals 0 implies the socle is not 0. So the socle has to avoid the intersection, and therefore it cannot be contained in all of them.
Is the maximal ideal n?
Yeah, this is the maximal ideal. Let me be. Okay. So this is the little lemma about the socle. If the depth of a module is 0, then there exists an n such that the socle avoids itself. That's an important conclusion to keep in mind. So that's this little socle guy that tends to show up in proofs like this in mysterious technical ways. So now, for this to be useful, we need to cook up a module that has depth 0. But that's there's a very standard way to do so. And so now let's look at R. Let's get back to R. And let's define Z as the depth of R. Right? R has some depth. Remember, it's the maximal length of a regular sequence in R. And so what that means is that we can cook up a regular sequence in R made of C elements, regular sequence. If R is Golden-Macaulay, this sequence is going to have rank D, you know. But there is a regular sequence. And we can define A, this ideal generated by a regular sequence. And the observation is that the depth of R is 0. Because if it was not 0, you can extend it. Or another way to think about it is like this regular sequence, since it is regular, the Kotul complex gives you a resolution of R modulo A of length n, and then by Auslander-Buchbaum formula, the depth of this module has to be 0. Okay, so there are many ways to see that. And so the whole point is then what is the conclusion? There exists n such that the socle of R modulo A as an R module is not contained in the extension of MM to R modulo A. So remember, you can think of this as MN plus A modulo A, right? Now what to think about it, but I'm going to use that notation just to be consistent. Is that okay? It's fine to be confused about it. I mean, it's a super annoying conclusion, right? But let's put it there. So there exists an N such that this is true. That's all I need you to remember. Okay? That's the key of the proof. But so far there is nothing. It's just making interpretations of the definitions of everything. Okay, but it's there. Let's put that N over there. Let's leave it there. Just now, how would that be useful for anything? I have a lot of head-log relationship with this level. I love it because it's kind of helpful, but I hate it because it's confusing to me. It just doesn't taste good to me. Now look at this lemma. This is the lemma 2.5 in the notes. Let's take a local ring of depth C. Then there exists N such that for all, this is like for all infinite minimal resolution. So take a module and any module, just a minimal free resolution of a module, right? Remember, this means that here we put like beta 0, which is the zero beta number, or beta 1m, or beta 2 out of m, and so on. And at some point, we reach to R direct sum. These are direct sums, direct sums, direct sums. Direct sum beta I of m pi. We call this not pi, right? Most of the time. Beta I plus 1 m. Right? So this is the lemma. So you take a ring R with some depth, and we suppose that it's not regular, right? That's the intuition here. And we have any infinite minimal free resolution. We consider all of them, right? They will look like that. The fact that it's minimal, remember, means that essentially you can think of these guys as matrices, and the fact that it is minimal means that the entries are elements of the maximum ideal. In other words, the image of this is inside the extension of the maximum ideal. Now, what does it mean that it is infinite? It means that when we look at phi c plus 1, that is not 0. Let me make that remark here. What does it mean that it is infinite? Being infinite means that phi c plus 1 no, what it means is, but it means, technically speaking, it means that, sorry, beta this beta c plus 1 of n is different from 0. Right? Because if it is finite by the Auslander-Buchbaum formula, this number is 0 because it has to stop at beta c. Which is the projected dimension plus that equals dimension. So you get this non-vanishing here. This is gonna be important later. Actually, for now on, I'm just gonna call beta I is gonna be this beta I n. Okay, now to the conclusion. What is the conclusion of the theorem? The conclusion of the theorem is that so phi c plus 1. The idea is to focus on phi c plus 1. Okay, phi c plus 1 is not 0. But the lemma tells you that it cannot be arbitrarily small, arbitrarily close to 0. So then, the entries of phi c plus 1 are not in m to the n, the maximal ideal to the n. But look at the order of the quantifiers, right? There exists an n such that for all minimal free resolutions, the entries here are not in here. You see, you may think, okay, I know that the entries of phi c plus 1 are not 0 for a given n. And then you may think, okay, but if I start to take modules, I may think that, okay, they get smaller and smaller and smaller, possibly. But this lemma says no, there is a lower bound on how tiny they can be. Right? In other words, well, so now we need to make an interpretation that is going to be used for the proof of what this means. In other words, so we're going to apply the lemma like this, but we're going to prove it like this, i.e., the image of phi c plus 1 is not inside m to the n extended to r plus bc plus 1. Remember that bc plus 1 is a matrix that goes from r direct sum to bc plus 2 r direct sum bc plus 1. Right? So we take the image and we're saying that it's not contained in this extension, which is going to be useful to think about mn direct sum bc plus 1. Remember, these bc are just these vector numbers. Sorry, I know that the proof is probably it's not so easy to follow. It's a little intricate. But we do it so far. Proof of the lemma. How are we going to do this? Who do you think is n? Right? The theorem says there exists n. Who is n?
The one from
there. Take n as before. So we take n as before. I.e., let's take n such that the SOCL of R modulo A, where A is generated by a regular sequence, it's not in here. Right? We're going to try to conclude this out of this, essentially. Where remember, A is and this idea is generated by a regular sequence. Right? So a regular sequence. Okay, let's see how this works. I think it's super cool. Let's go the way back.
Oh, right. So, sorry, before we continue.
Yeah.
Are the bees on the top of the, right after the image of is are the bees the ones that we
Exactly. All right, by definition, it's just, I just don't want to write beta I and capital just bi. These are the beta numbers. So what's the thing? The thing is that so what? First, an observation by the Auslander-Buchbaum formula. We know very well what is the projected dimension over R of R modulo A. It is. If you add the depth, you get the depth, right? So this is C. Because the depth of this module is 0. So projected dimension plus depth is the depth of the ring, which we call C in here, right? Or another way to see it equivalently is that, well, it is generated by a regular sequence. So the Kotzul complex is a minimal free resolution of length C. Okay, so there is that. And so it means that if we try to compute the Tor at C plus 1 of M RA, this is 0, right? Because if we take a minimal free resolution of here, we know that it goes at most to length C, and therefore when we look at the Tor at level C plus 1 is 0. Okay. So this has important conclusion. Take the minimal free resolution we started with and do a base change by R modulo A. In other words, take that sequence and go modulo A. Right? This is this module here is not flat. Very generally, quotients are not flat, so exactness is not respect. But the failure of being exact is going to be measured by this Tor. So in many places, the sequence we get is not exact, but given that this Tor is 0, there will be a very special place where it will be exact. So which is the following step. So you do this base change and you get a huge thing, right? So let me write it down. So you're going to have a whole bunch of things, but I'm going to concentrate on a particular step. Right? Well, this goes on, right? Forever. Well, not forever. It stopped that way, but it's going to go forever here, right? So we get that. And the failure of the exactness at this point is measured by who? By that Tor. Okay? Because how you compute this store, right? Like you take a minimal free resolution of this, you can do it like that too, which is there. And so this store is 0. So it means that this is exact here. Exact here. This point. Aha. Well, what does that mean? In more down to earth terms, that means that the kernel of VC modulo A of this map here, right? The kernel of this map is contained in the image of C plus 1 modulo A, right? The other inclusion is always true, but this inclusion is the one that that means exactness, right? Because the homology at this level, right, is the kernel of this modulo the image of this, and that's 0, so you get the other inclusion. However, and here's the important detail, the resolution we started with is minimal. So the entries of VC are all in the maximal ideal. So who is inside here? Who, well, yeah, I guess people on Zoom can see. Who is inside here? Inside here, you have the socle of our modulo A, right, at every single entry. It's a submodule. But what is the property of these guys? These guys don't tolerate to be hit by elements of the maximal ideal, right? By definition, they all vanish, right? When they get in contact with the maximal ideal. In particular, they vanish when they get in contact with this matrix. Because this matrix here, the entries are elements of the maximal ideal. So if you take a vector here with entries that don't tolerate the maximal ideal, and you put them together, they vanish. In other words, the socle of our modulo A is inside here. C plus 1. Right? So this guy is inside here.
Question, in order to make that a little bit.
Yeah.
So the reason why the socle is only in that segment of the sequence is because of the exactness of the ring in that part?
This inclusion here?
Yeah, because of the exactness of that part?
No, so the socle is always inside here.
Okay, so yes.
Yeah, the socle is always a submodule.
Yeah.
Right? By definition, this socle is inside this ring,
yeah.
By definition. These are the elements in here that are killed by the maximal ideal.
So my question is a little bit oriented into the fact that for every entrance for the sum in the sequence, is there going to be a socle such that they vanish for all maximal ideals? For example, if I go to the next part of the sequence of, for example, is there going to be a socle over there and defined such that they all vanish in the maximal ideal?
I don't understand the question. So this module has a socle.
Yeah. So that's my question. Like, could we do the same argument for each entrance of the sequence?
So yes, it is true that the socle of every element of every module here, they are inside the kernel of the map that follows. It has nothing to do with this specific spot here.
Okay.
Yeah, so this observation that this socle is inside the kernel is very general, and it holds for every single entry. The exactness is used here. This is very general, exactness is used here, and you get this inclusion. Yeah. So what are we trying to prove? Right? We're trying to prove that this image is, well, that this image, the image of C plus 1 without this modulo A is not inside that. Suppose, for the sake of contradiction, that it is. That would imply that the image of this guy will be inside m to the n r to the, what do we say, bc plus 1 modulo A. Well, you can think of this as n r modulo A, entry by entry. So if what we want to prove is not true, it would follow that this thing is inside there. But this number here, because the sequencing is infinite, is non-zero. That's very important. Because if BC plus 1 is 0, we're making statements about the empty set. Which, like, right? The point is that we indeed have direct sums. So because of this is not 0, it's a very important thing. So the theorem doesn't apply, the sequence is not infinite. And you can see why, it's right here. Because you need that this is not 0 to conclude that then the suckle of R modulo A is contained in n R modulo A. Which is a contradiction. Okay? You see why it's important that this is not 0 to go from here to here, right? If this is 0, then direct sum over the empty set is the 0 module. So I love it. Like, right? It's subtle detail, but it's the beauty of math. Right? These little details. Right? Okay, so that's the lemma. Any questions so far with this proof? It's a great lemma with a great proof. Okay, I claim that this lemma essentially implies the Kunz's theorem. Somehow. When you want to prove a great theorem, it has to be a consequence of an even greater one. Okay, we have a lemma that says that if we have minimal free resolutions, we can find a bound for how non-zero the entries of the C plus 1 matrix are, right? Okay, now let's go to Kunz. Back to Kunz. This is the hard part. We are going to assume, so take R, comma N, comma K. You can take it complete if you want, but we don't need it here. So local ring such that Frobenius is flat. In other words, base change by Frobenius is flat. If you have an exact sequence of R modules and your base change by Frobenius, you get an exact sequence of R modules. Okay. Okay, what do you think we're gonna do? Suppose, for the sake of contradiction, that R is not regular. Suppose that R is not regular. What does that mean? According to what we spent a week doing, that the residue field has infinite projected dimension. In other words, you can find, a minimal free resolution of the residue field is infinite. right? So in other words, you can have the residue field and you construct the minimal free resolution. The zero Betti number, the first Betti number, and so on, is infinite. In other words, the Betti numbers of the residue fields are never zero. That's what it means to be non-regular, right? To be singular. So, but Frobenius has something to say about it. Well, I guess let me write down here. Well, let me say here, right? This is the usual notation. So we're going to call this matrix P0, P1, and so on. We use the usual notation. Okay, you have one, right? So how can we use this hypothesis? This is flat. What does that mean? It means that if you do a Frobenius base change, you get something. You get exactness. So if you take a Frobenius base change of this, you get a minimal free resolution. Let's do it. So let's take that and let's do a Frobenius base change. So base change by Frobenius. What does that mean? What is the base change of this? Of K along Frobenius? Remember, this is R modulo M. If you base change by Frobenius, this will be R modulo the extension of M across Frobenius. So M, so it would be R modulo M to the cube. The Frobenius power of the maximal ideal. So if you do that, what you're doing is cooking up a minimal free resolution of these modules. So you will have the exact Betti number, the same Betti numbers, R1, beta 0, beta 1, K, sorry. But we get new matrices. What happens to the matrices when you do a base change? They get raised to the p power every single entry, right? So this is the exotic thing about Frobenius, the target and it's the same thing. But in general, like if you have R2S, right, and the map is theta, and you have a free module, then the base change is just raising by that. So let's think about it. Suppose that we have a map between three modules of rank 1, that's multiplication by something. Suppose that you do a base change by S, then you get S maps to S, and what is the action of R? Is the action of R on S, but along theta. So it's in principle is theta of R. So when you apply to Frobenius, right, what happens to the entries of the matrices is that they are all raised to the qth power. It's the same action of the matrix, but with the R module structure given by Frobenius. So there will be matrices here. I'm going to call it beta, phi 0. I'm going to call it to the q. Phi1 to the q, where phi I to the q is equal to is the same matrix, is phi1 phi I, but with entries raised to the qth power. Okay? But since Frobenius is flat, the whole point is that this is exact. So this is a minimum free resolution. So this is a minimal free resolution because Frobenius is flat, right? Base chain of Frobenius preserve exactness, and for it to be minimal, all it had to do is for the entries of this matrix to be the maximum ideal. But actually, what is the point? The entries of phi q are inside which ideal? M to the cube. Right? All you did was, all you do is you take the entries of phi, which are in the maximum ideal, and raise them to the cube power. Therefore, they live here. And moreover, they live here. M to the cube. For all I. Now, in particular, for I equals C. C plus 1, I think. Where is the contradiction? We found a family of minimal free resolutions, right? They're indexed by E. For every single E, we found a minimal free resolution where the matrix in the C plus 1 spot, in the C plus 1 arrow, are all contained in M to the cube, sorry, M to the cube. So they get arbitrarily smaller, contradicting the previous lemma. Because the lemma says that they cannot get arbitrarily small. Right? You see? The lemma said, right? I think I erased it. That there will be an n such that whenever we have any minimal free resolution, you can think of the matrix C plus 1 is not in M to the n. But here, all you have to do is to take E large enough to violate that. So that's a contradiction with the lemma. And that's the proof of the Kunz's theorem. It's really cool, I think. And the other thing I want you to appreciate is that this proof justifies the first week we had about characterizing regularity in terms of projected dimensions. Because what this proof does is equates the flatness of Frobenius and finite projected dimension. Okay, so that's what I was saying, that's the right way to think about regularity. And I think Frobenius also agrees with that. Okay, any questions so far? The proof is absolutely beautiful, isn't it? It's very delicate.
I didn't quite understood why we went from that contention of the n to the qth power to the other one.
It's just because in the lemma we had ordinary power, right? The lemma said that the entries are not in m to the n.
Oh yeah.
Yeah, I was just remarking that the Frobenius power is always inside the ordinary power.
Okay, yeah.
So that it violates that it's contained in m to the n.
Okay. Yeah. Okay.
It's just
But I agree, it's super cool.
So yeah, so beautiful theorem with beautiful proof. And now you know it. Most people don't. Any questions with this proof? What else can be said about this proof? But yeah, that's the proof. You start with a minimum tree resolution. Since you can iterate for it, it's very important too. You can iterate, you can do base change of that, and you get a ton of minimum tree resolutions, but whose matrices get arbitrarily small. And we had a previous lemma sort of saying that that's not possible. So you could say that the lemma is stronger than Kuse's theorem somehow. You can say that Kuse's theorem is a corollary of the lemma. Well, the hard direction of Kuse's theorem. Okay, so if you don't have any more questions, we can move on now from Kuse's theorem. We're all happy with it. Okay, great. So the contradiction there, I think. Maybe on Zoom. Okay, so I would like to mention a few more Kuse's theorems. Oh, here's a question that could be, as far as I can see, is open. No, let me just move on. Okay, relative Kuse theorem. So what we just saw is the so-called absolute Kuse theorem, but it's also a particular version of this one I'm going to write down, which is the last one. So so definition is the notion of regular algebra. So for this is a notion of regular algebra. So you may think that regularity is an absolute notion, which it is, but it has a relative version. So take what is the notation I'm following here? R2S, I guess. So let's take R2S and R algebra. You can call it beta. So it is regular. So what? If first thing, R and S are Noetherian. Okay. Second is flat. Or faithfully flat? What did I say here? I think it's flat actually. It's flat. Remember that flatness intuitively means that a good behavior of the fibers. You know, like when you move along the fibers, there's a good behavior. That's the idea. So it's flat. So this is good behaviors along the fibers. And so the third condition, it has to do with the fibers being actually regular, like being smooth. So what is a fiber? So fibers. What is a fiber, right? You take R to S and or admits a map to the residue field at any point P, at any prime ideal P, right? You localize a P, and then like you go to the residue field. So there is a surjection like that, right? Yeah. Actually, I'm not sure if this is surjection, but there is a map. Sorry. So this map is you localize a P, and then you take the quotient, the residue field, right? And so what is the fiber? The fiber is this leg here in this Cartesian diagram, right? That you take KP tensor with R, right? This is the fiber. This map here is the fiber. The fiber is this ring, which is a KP algebra. The fiber. This is the fiber. Okay. I'm gonna denote it by S sub KP. Okay. You guys remember this definition of fiber? Okay, what about the fiber? The fibers, should I go to the other side? So sorry, Harden and Werner. I feel every time we go to the other side, it's helpful for the people on Zoom. What about the fibers? The fibers are geometrically regular. So the third condition is that the fibers are geometrically regular. i.e., what is this geometrically thing here doing? So you have your fiber, right? Which is a kappa P algebra or KP algebra. That's the fiber. So being geometrically regular means that this ring here is Noetherian. Sorry, it's regular, in particular Noetherian, but that property is preserved even if you do a purely inseparable base change. Okay, so it's okay, let me write down the strong definition. So take any finite generated field extension, any finite generated field extension, and you can do a base change, right? You can do another Cartesian diagram here, and I'm gonna call that SL, right? SL is L tensor kappa P is kappa P. Okay, by definition. So geometrically regular means that this SL is regular for all L. You see? But in particular for L equals kappa P, it means that this one is regular, in particular Noetherian. It's not true that the fibers will be Noetherian in general. It's part of the definition that they are. Okay? So the fibers are regular even if you take any base change like this. So the idea is that these are fibers too, right? But these are fibers by L points. So if you know some scheme theory, you see that these are also fibers. So we're saying like really, all fibers are regular. So actually, just as an observation, to check this property, you don't have to do it for all finitely generated field extension. All you care about are the finite purely inseparable ones. Those are the ones that can possibly destroy regularity. Separability never destroys regularity, that's the point. So you have to check only finite purely inseparable ones. Okay, but there is this notion of regularity for algebras. Okay? That generalizes, if you want, the classical one. Because if you have an algebra defined over an algebraic closed field, it is regular, for example, if and only if it is geometrically regular. Right? So, is this definition okay? Any questions so far? Okay. Now, let's take the same algebra we had, R2S theta. And last time we were talking about how you can take Frobenius, right? You can take Frobenius here, and then you can do this base change. Right, but then you have Frobenius here, and you have the push forward along Frobenius theta, right? This is Frobenius, this is Frobenius. And therefore you have a uniquely well-defined map here that we call the relative Frobenius. This is the Frobenius of theta itself. It's the Frobenius of a map. It's not the Frobenius of a ring. It's a relative Frobenius. So then there is this version of Kunz's, which is called Radu and Red theorem, or relative Kunz, that says you can ask, well, when is this map flat? F theta E is flat if and only if, what do you think? Theta is regular. You see, it's a Kunz's theorem for maps, not just for rings. But actually, the absolute Kunz's theorem follows from this one. Because the absolute Kunz's theorem is nothing but the relative one when R is just Fp, right? Every ring of positive characteristic is an Fp algebra. And regularity of an Fp algebra is actually regularity of the ring, because Fp is perfect. It has no finite purely separable extensions. Okay? So, and so I would like to say a few words about the proof of this. So it may look like more general, but actually the proof is based on Kunz's theorem. So the way the proof of this result works is to argue that you can restrict the fibers of the map. That to prove either side, what you do is that you restrict the fibers. Okay? And so, for example, you're going to rely on something that is called the criteria for planitude and fibers. But in order to do so, you realize that a whole bunch of things have to be in the theorem. That's the hard part of the theorem. And so, for example, the hard part of the theorem is to prove that if you have a regular ring, a regular algebra, sorry, this ring here is in the theorem, which is far from obvious. But it's true. And that's really the hard, and the rest is rather formal, really. The hard part of this is Noetherianity. And then you can argue that you can restrict the fibers, and when you restrict the fibers, essentially what you're doing is the absolute Kunz. Okay? So the proof is take absolute Kunz. So the proof is arguing why it suffices to prove the absolute Kunz first. But that argument is hard because the Noetherianity issues. Right? So we won't get into the proof. But what this suggests in principle is that you can have a theory, a relative theory of F-singularities as well. But we won't get into that because that's somewhat delicate. If I have 5 more minutes, which I think I do, I would like to talk about another generalization of Kunz's theorem, which is the following. So it's a beautiful, beautiful result by Barkov and Peter Scholze. So, well, I don't know how much you read the news, but you may have heard that Peter Scholze was a field medalist a few years ago. And well, I don't know if you know about Barkov. Barkov should be a field medalist, to be honest. So. Yeah, they had this great theorem, which is a generalization of Kunz's. I'm going to tell you why, but we won't prove this theorem, which is not particularly hard to prove, But well, if you know them, you know that they wrote it down in the language of the right categories, which is the language that makes this proof easy. We could do that, but we'll have to get into that, or unravel the proof in terms of non-derived terms, but it did get super hard. So I decided not to go through the proof. Maybe at some point I will just add it. But it's the following. It says, they say, okay, let's look at the hard proof of, the hard part of Kunz's. So what is that hard part? So theorem. So you take R comma n, a complete local ring. So the hard part of Kunz's theorem, right, is to prove that if Frobenius is flat, that this ring has the residue field has finite projective dimension, right? In the complete case, this applies us to do the complete case. So they say, well, this is also true. In a sense, this is an analog to the lemma we just had. They say that then the perfection R curve. Let me write it down like this. So the perfection, this is the one that is lower. Yeah. The co-limit perfection is also called. So what you do is you take the co-limit of Frobenius. Right? So you can iterate Frobenius all you want, right? That's the power of it. And you have this sequence of things here, right? And therefore you can take a co-limit. Right? Think of this as that ring that contains all the possible p powers of R. It's a huge ring, it's perfect. It's virtually never Noetherian. It's only Noetherian it's still. They say this has finite global dimension. Actually, it also has finite dimension. And finite dimension. Actually, it has the same dimension of R. Essentially, because this ring map here is purely it's a homomorphism, the perfection. So notice that this ring here has finite global dimension, has finite dimension. It's essentially a regular ring. What is missing for it to be regular? That there is Noetherian. That's the only thing that's missing. And so this map here, since it is a co-limit of faithfully flat maps, well, if Frobenius were flat, would be faithfully flat, okay? So this would be faithfully flat if the Frobenius of R is flat. So they would say, it would be a faithfully flat extension to a perfect ring if Frobenius were flat. So this is why this is a much more general thing. I'm gonna prove in a second. But that's what they have. They said your ring and it's a map to this ring that is essentially regular. All that is missing is Noetherianity. Right? So if you're willing to drop that assumption, you can call it regular. Right? That's what we're talking about the served point of view of regularity for Noetherian rings. So they have this absolute beautiful thing, and therefore that implies Kunz. Oh, we don't have the time. Let me do Kunz real quick. So why does this imply Kunz? Let's do it real quick. So this implies Kunz, easy peasy, lemon squeezy. Implies Kunz. Why? Because according to Kunz, all you have to do is to prove that how to do it. This is 0. For I, where is the I? Here or here? Here. For I sufficiently large. Right? That would mean that this has finite projective dimension. Everything that the ring has global finite global dimension. Right? To prove that this is 0 after a certain point. But if Frobenius is flat, then its perfection is flat, it's faithfully flat. So you can do a base change to the perfection, which is flat. Therefore, it's going to commute with Tor. You can take the module to care about. You can base change it to the perfection, but it is faithfully flat. It's gonna commute with Tor. And so all you have to prove is that this is 0 after a certain point. But it is. Because the theorem says that the perfection has finite global dimension. So this has to vanish after the global dimension of that ring. That's it. That's it. But you need the planets to that base change properly. Right? And in fact, if you give me, I'm going to just say it works. This motivated the so-called PI Kunz's theorem, which is the Kunz's theorem in mixed characteristic. It says, maybe you need a complete local ring, I forgot, but it's a theorem by Lingshama, Shika-Iyengar, Bhargava. I hope I'm not forgetting someone there. But they had a theorem that says that essentially, let's say complete local ring of mixed characteristic, perhaps over, so that it doesn't over like a ramified, DBR, something like this. It's regular, if and only if it admits a faithfully plasma chain, not to a perfect ring, but to what? To a perfect ring. So that would be the Kunz's theorem in mixed characteristic. Take that theorem, replace it perfect with a perfect point, and you get what this should be true in mixed characteristic. Okay? So that would be the other version of this theorem. Well, let's stop here. Sorry for taking moments. So that ends the discussion of Kunz's theorem. No more Kunz. Next week, on Thursday, we're going to discuss F-finite rings. So now we understand what regularity means. And the next step is introduce very good finiteness conditions. And that's going to be the notion of the finite. And with that in place, we are now ready to talk about F-singularities. Okay, see you on Thursday.